So today's topic is rigid body in planar motion. We start with the definition of planar motion. A rigid body B is said to be in planar motion if each of its particles moves in a plane and all these planes are parallel to one another. For example, a hockey puck is a rigid body and say it is sliding on ice, then it is in planar motion. The ice is horizontal, say. Now suppose a rigid body is undergoing planar motion and you choose a particle in the body and you want to know its velocity. How do you do that? For that there is a method, and the proof of that method will be found in chapter 16. Let's see what that method is. Say this is our rigid body B, this rectangular plate, some metallic plate, something whose particles do not change relative position as the body moves. It's rigid and it's undergoing planar motion. It is moving in this plane in some way. Okay, it may also be undergoing rotation, it is also sliding, something is happening. Say you have chosen an arbitrary particle P here and you want to know the velocity of P. How do you do that? The method involves first choosing some reference point, any point in the body. Say you have chosen this corner point C as our reference point. Well, if you want, you can choose P itself as your reference point. There is no restriction on that. You can choose any point as your reference point. But say C is our reference point and we want to know the velocity of P. The method first involves looking at the velocity of C itself. It is the particle, it will also have its own velocity. Say that velocity is this Vc, which is this vector. Okay. So it has some magnitude and it's in this direction. At some instant, it may change, but at some time instant, this is the velocity of only that particle C. Okay. And this velocity is going to contribute to the velocity of P. But there is some other contribution also. If for a moment you assume that C is not moving, or say more accurately, you are moving with C, so that when you look at C, it looks as if it's fixed with respect to you. Then what you do, then you see how P is rotating about C, or the same thing, how the rigid body is rotating about the point C. Because you are fixed with C, you are moving how C is moving. So C is fixed for you, and then if you look at the rigid body, there may be a rotation. Still the body is changing in some way, so then there will be rotation. Say the angular velocity of that rotation is omega, and say it's rotating like this. About C. About C means what? About C means the axis of rotation passes through C and is perpendicular to this plane. Okay. Then that's a general circular motion, a rigid body rotating about a fixed axis, general circular motion for the point P. Okay. And that general circular motion will give P a circumferential velocity. Let that circumferential velocity be this Vr. Okay, so it's rotating like this. So at some time instant, say this is the velocity of P, circumferential velocity of that rotational part of the motion. So this is your Vr and this is that Vc. So you take the vector sum of them and that gives you the velocity of P. Why does this method work? I mean, what is the guarantee that this is actually the velocity of P? That will be proved in chapter 16. Let's accept this for now and let's apply it to an example and see what we can do with this. Example 210, a circular wheel of radius B rolls in a straight line on a fixed horizontal table. A wheel rolls like this in some direction in a straight line on a fixed horizontal table, and the wheel is circular, of course. We have to find the velocities of the particles of this wheel. So the wheel is a rigid body in which you arbitrarily choose any particle, you have to say what its velocity is at some given time instant. So this is the diagram. Say this is our wheel. I have tried my best to draw a circle, but I cannot really draw very well. But anyway, this is the circular wheel which is rolling like this. It is moving rightward and it's rolling on this horizontal table. We have chosen the center of the wheel conveniently as our reference point, and say any particle in the wheel is this P, which is some arbitrary particle some distance away from C. I did not write the distance here. The distance is say rho because it's a bit cluttered. So what do we see here in this diagram? What are the ingredients of this? Ingredients means what are the parts of this diagram? You see this vertical line, dashed line, with respect to which we seem to have shown the angle that this line makes. Okay, this line makes an angle theta with that particle. What is this line? This is the line obtained by joining C and that particle P. And say the length of this line is rho. So if the angular velocity with which the wheel is spinning is omega, so that is fixed, then the circumferential velocity of P that you already know is rho omega. And at the same time, C has this speed u with which it is moving rightward. And this q is the bottom point. We have also shown the directions of our usual unit vectors I hat and j hat. Okay. So this is the circumferential velocity of P, and this is that Vc, that velocity of the reference particle. So that means we now have to add these two vectors. This is actually not a vector. It is the speed, it's the scalar. The vector will be u times I hat because it's in that direction. So you have to add this one and this one. This one is also not a vector. This one is a scalar. You have to multiply this with the unit vector in this direction. Then you will get this vector, which actually is the circumferential velocity. Then you add those two vectors, and by that method, that will be the velocity of P. So now what we have to do is we have to find the unit vector in this direction. How do we do that? We note this fact that the angle between u and this vector is also that theta, equal to that theta. Why? Let's see that here more clearly. So this angle is theta, and we are saying that this angle is also theta. What is the relationship between this line and this vertical line? This is horizontal, that is vertical. So that means you obtain this line from this one by a 90-degree clockwise rotation. What is the relationship between this line and this line? They are also perpendicular to each other. Why? That's because what is this line actually? This line is along one of the radii of this circle, and this is along the tangent. Okay, so that's why they are tangent to what? Not tangent to the wheel, but if you draw a circle on which P lies and whose center is C, this will be tangent to that circle at P, this line. So that is why this is perpendicular to this. So that means from this line you will get this if you turn clockwise by 90 degrees. So the angle between these two things remain the same if you turn those two things, both of them, clockwise by 90 degrees. So that is, and that just gives you this angle. So that's why this is also theta. But how does this help us? This is how it helps us. You slide this vector parallel to itself, so then it stays the same. And I mean, you just slide the entire angle itself down in such a way that the vertex coincides with the origin. Origin means in this case that is C. So then you have theta here. Why did I write minus theta though? That is because it is like this. I mean, you have to see what the angle is that this is making with the positive direction of the x-axis, or in other words, in the direction of our I hat. So that involves clockwise rotation, which means negative angle. The magnitude of the angle is theta. This is the geometric angle. So that's why I wrote minus theta. And once you have found this angle, then it's simple to write the unit vector in that direction. Why? Because on the unit circle whose center is C, the point that will lie at the intersection of that circle and this line, this vector, will have coordinates cos minus theta, sin minus theta. So if you take that point and find its position vector relative to C, that vector will be this cos minus theta I hat plus sin minus theta j hat. So this is that unit vector in this direction. So now we can write the circumferential velocity of P, and of course also the velocity of C, which is a simple thing, u times I hat, and then we will add them. So these are the velocities. The velocity of C is that simple u times I hat, and the velocity contribution that P gets because of this rotational motion is circumferential velocity, which by definition is a scalar, but we want a vector, so we multiply that with that unit vector in this direction, which is this. Now cos minus theta is cos theta and sin of minus theta is minus sin theta. So you have a minus sign here. Now we will add these two things up, and that will be the velocity of P. And that velocity is this. The velocity of, this is how the author has denoted the velocity to emphasize that it's the velocity of P. He has written P here. Vp vector equals this. So you add these two things up, u plus rho omega cos theta times I hat minus rho omega sin theta times j hat. Now in particular, say you take rho equal to b. Rho equal to b means now P lies on the circumference. That means the distance of P from the axis of rotation is equal to the radius. And at the same time, say theta is equal to pi. So that your P actually lies here. It's the bottom particle Q at some time instant. In that case, what happens to this formula? So we get the velocity of Vq. So in place of rho you will put b, and in place of theta you will take pi. Cos pi is minus 1 and sin pi is 0. So this component will not be there. We will have only I component, and that will become u minus b omega. U minus b omega times I hat. Now the author did not consider this special case simply for nothing. There is a reason. What is given to us about the wheel? That it rolls on the table, it does not slip. Had the provision of slipping been there, say if the table was very slippery because of some substance, these two quantities u and omega would not have been related. Because it's given that the wheel rolls, they are actually related. We will see how, but let's consider for a moment that this can slip. Then why are these two things not related? What is u? U is the speed with which the wheel moves rightward. It's that linear speed. Whereas omega is the angular velocity. It measures how fast the wheel is spinning about its own center. Now maintaining u, if you want to increase omega, say you want to make the wheel spin faster, that can be possible only when it slips on the ground, on the table I mean. Otherwise it's not possible. Similarly, maintaining that same omega, if you want to say speed up the linear movement of the wheel rightward, then it has to slip. Okay, do you see that? But because it's given that it has to roll, so now these two quantities will be related. Let's see how. Rolling requires this, that the velocity of q actually is 0. If the wheel slips at any moment, every particle is actually spinning. So there is a velocity. However, if it is rolling, the moment this particle becomes the bottom particle, at that instant, actually it's not moving like this. Okay, at that instant it does not move. So that means this must be 0 or omega must be u divided by b. So they are now related. Omega has to depend on u. And now we are going to use this fact here. So using this in the original velocity formula, and after some little simplification, this is our velocity. U times 1 plus rho over b cos theta times I hat minus u times rho over b sin theta times j hat. And now again, in particular, if we take rho equal to b, that means say our particle p is on the circumference, not necessarily here, but somewhere, then rho divided by b becomes 1. So these parts vanish and this becomes the velocity formula for p. U times 1 plus cos theta I hat minus u sin theta j hat. Now next let's calculate the speed of p from this, the speed of a particle on the circumference, and let's see what the speeds of the other particles on the circumference are. This one we have already got from rolling that it has to be 0, but what about the other particles? Speed is magnitude of velocity. To avoid writing square root, I have taken square of magnitude. So this square plus this square. Obviously it won't have I hat and j hat anymore. So that is this, which turns out to be this. I did not do a detailed calculation because you probably have seen this many times already in different places. So it becomes this, and then we take square root, and keep in mind that here you can just simply write 2u because 2 and u are positive. U is speed. The cosine term, however, may be negative. So that's why we have kept the absolute value bars here. Now let's see if we really get what we started with. I mean, does this support the fact that the speed of q should be 0? Q corresponds to what? Already see, this is the speed of some general particle on the circumference and q is on the circumference. That is okay. But what's theta here? In this case, theta is pi. For q, theta is pi. And cos pi divided by 2 is 0. Yes, actually that is 0. And what about the topmost particle? For the topmost particle, theta is 0 and this term becomes 1. So there you have maximum speed. Okay, so as the wheel rolls, actually the particles on the circumference don't have the same speed. At the bottom there is no speed, at the top there is maximum speed. The top particle of course keeps changing. At some given instant it is something, the next instant it is something else. But that's the top speed. The video ends here. Next week we are going to see frames in relative motion. Say you have two frames of reference which are moving relative to each other in some way, and say you have a particle. Now you can measure the motion of the particle relative to one frame. You can also measure the motion relative to the other frame. How are these two measurements related?